It weighs about a kilogram. It has no wings, no helicopter rotor, and somehow still it can almost perfectly hover in a place. So, how? This is the first video of my video series of how to build your own DIY drone. This video would be particularly about the physics behind a drone, because before we build a flight controller, we need to first understand the machine we are trying to control, the dynamics behind it, how actually the forces act upon it. So here on the whiteboard, this is a pictorial depiction of a drone. This is just a rough sketch of how a drone looks like. A hovering drone is in equilibrium. The total thrust is equal to its weight. There are basically three forces that act upon a drone: lift, gravity, and torque. Lift is the force that is created by the motors pushing air downwards in order to oppose the gravitational pull or the gravitational force. When the lift becomes equal to or greater than the gravitational force, the drone starts to hover or fly. So now there is something known as TWR. TWR is short for thrust to weight ratio. This is basically just the ratio of the force in grams of or kilograms that you measure that the motors are producing upwards by the force of gravity pulling the whole quadcopter downwards. Now, why is this TWR or thrust to weight ratio important? So what happens is, theoretically, if my thrust is equal to mg, that is the gravitational force, then my drone is in equilibrium and it is practically weightless. But it does not mean that it will start flying. That is just the point where the drone starts to hover. If we want to make a drone fly and fly well, we need at least a TWR ratio of 2:1. 2:1 ratio drones are quite large. They have a high moment of inertia and they are very much more efficient in comparison to small 3-inch, 5-inch or 7-inch FPV quadcopters, the ones you see for racing. Those quadcopters are really fast, really agile. They have a TWR ratio of 20, 30 or sometimes even 50 or 100:1. But for this drone, I chose it to make a trainer drone as it is more efficient and it is easier to control for a beginner. Now, to understand the role of torque in this whole equation is that torque is basically a rotational force, and if you look at a drone motor from above, it's rotating. So the direction in which it is rotating, for example, let that be clockwise, then by Newton's third law, it would also produce an opposite force of rotation or rotational force on the drone itself. That is torque. So now if all the motors were rotating in the same direction, then we would have a net torque of, let's say, value x. So now the result would be that the drone is spinning in that particular direction without any control, and the user cannot actually control that drone. That is the reason that we want two of the propellers to, let's say, run in clockwise direction and the other to run opposite, so that all the torque between all the four rotors gets cancelled out and we have got a net torque of 0, which ensures that the quad does not rotate endlessly and can be controlled by us. So how do you control a drone? How does it move? Basically, a drone has 6 DOF. DOF is short for degrees of freedom. So these 6 degrees of freedom are in 3 axes: X, Y and Z. The X axis corresponds to roll, which is the left to right movement. The Y axis corresponds to pitch, that is the front and back movement. And the Z axis is responsible for yaw, that is rotating with respect to an axis passing through the center of the drone. So if you ever see a drone rotate with respect to an axis passing through the center, that's just the yaw movement. So how do you make the drone move? So it's quite simple. We basically use differential thrust. Differential thrust is nothing but just imagine you need to make your drone go forwards. So what do? You increase the thrust of the rotors behind so that the drone tilts forward. So by using basic trigonometry from class 10th, we could see that the force can be broken down into two components: F cos theta and F sin theta, where F sin theta is responsible for keeping the drone upright, whereas F cos theta would be responsible for making the drone move forward. All of these can be similarly replicated for all the four movements, whether it be left, right, front or backwards. The interesting degree of freedom or the interesting degree of movement is yaw. How do you make a drone yaw? So as we have discussed previously, we want the net torque of the drone to be 0 so that it does not keep on rotating endlessly. But this is also the force that helps us make the drone yaw about its axis. We can control the net torque and the direction of the torque acting upon the drone, and thus we can move it clockwise or counterclockwise about its axis. So physics tells us why the drone flies, but it does not tell us how it is kept in the air. So in the next video, we would be discussing the electronics that were used to make this DIY custom flight controller drone and why did I choose those specific parts.